Hello and welcome to College World. We're proceeding with our amazing beneficial C3 tutorials in order to ensure that you can get an A star. We're here in our third chapter of C3, which discusses a new function, new types of functions, which is the exponential function and its inverse, also known as the logarithmic function. So chapter 3, as I said, discusses exponential functions and logarithmic functions. And in this tutorial, we're going to be covering multiple aspects. First of all, we're going to have a brief introduction of what they are. We want to know their general formula. We want to know what the natural logarithm is and what's special about it, or the natural exponential function is and what's special about it. After discussing that, we're going to know the major graphs, the actual basic graphs of exponential functions, and then we're going to do some very remarkable transformations, ones you can see often, just to remind you of how to transform. And then after doing the graphs and the transformations, we're going to look at certain applications for the exponential function. There are multiple applications in many fields for exponential function, and we're going to take examples that come in books and past papers regarding this question. After that, we're going to go to the inverse of the exponential function, also known as the log. We're going to know that also it can be ln when we're talking about the natural exponential function and the natural logarithm. Then when we're talking about that, we're going to also discuss graphs and applications, although they're technically the same. And that would be it for chapter 3. It's quite easy. It's just making you get familiar with this new type of function, because we'll later use it in differentiation and integration, and it's one of the most important functions in the fields of sciences and economics. So let us get to the first part, where we discuss what the exponential function is. From its name, you know that exponential functions would deal with some sort of exponent. And this is exactly why its general formula for exponential function is a to the power x, where a is any real number. So you've got 2 power 3, 5 power 6, all these are exponents. Now if the exponent is a variable that changed, so you have 2 to the power x, 3 to the power x, all these are what we call the exponential function. Let's take here an example. So we're talking about 2 to the power x. If we're starting by x 0, 1, 2, 3, you will notice that you're going from 1, you're becoming 2, you're becoming 4, and then you're becoming 8. It is something that increases exponentially, and this is why it's called the exponential function. And if we want to draw it, we have here, so we want to know the general graph. We are going to have our x and y axes here. And as you see, we started from the point 1, and then we became 2, and then we became 4, and then we became 8, and we're increasing with the curve. The slope is increasing, the gradient is increasing. It's not just a straight line. And if we want to even take the negative side here, you're going to see that it became half. So in other words, this one is going to be some point here. But you will also know that there's no number that 2 to the power is to that number will give you 0, which means our x-axis is actually an asymptote. So if we draw it this way, we can note that this is an asymptote. It will never be negative, 0, and it will also never be negative, because simply you can't, 2 to the power nothing will give you negative unless the 2 itself is negative. Hence, this is the shape of our graph. It's an it's a graph with an increased slope in order to give you this curve. And then we can move on to our second graph. Here, because this is actually the general graph for a greater than 1. Now if we apply the same thing instead to a between 0 and 1, oops, this is not how you write a between 0 and 1. You're going to say here, let us take an example. So half to the power x. Negative 1 is going to be 2, 0 is going to be 1, 1, 2, 3, this is going to be half, quarter, and 1/8. As you see, as the x increases, our y decreases, and it also decreases exponentially. And this is what we call an exponential decay. Our graph will look instead like this. it will look like this. Our x-axis will still be an asymptote and it will never go to the negative side. And this is, as I said, an exponential decay, while this is an exponential growth. This will come in handy in the applications. Now, you will be thinking, hey, but does that mean I will never have the graph be on the negative sides? This is where we move on to the transformations. But before doing that, I want to tell you something. Here, this will be explained later, but you need to know that, not now, but d to the power, if you want to differentiate a to the power x, you are going to get ax ln a, and you'll know what ln a in a while. But as you see, this is actually a constant, and here, if there there is a certain number here that will make that if we differentiate a to the power x2 with it, we're going to end up with ax into 1. We want to know what if you want to know what the number is that you differentiate by itself in order by differentiate to get itself, this is the number e. E is actually a normal number. It has a value of 2.718, and it's more, it's just endless. So this is what we call the natural exponent, the natural number. And this is why when we're doing ex, this is the natural exponent, exponential function. And then we're going to see that its inverse is going to be the natural logarithm. So anything with e is going to be referred to as natural. And this is why it's an important number that we'll be using on later in the rest of the tutorial when we're talking about transformations and natural logarithms.